This presentation is an introduction to dynamic force analysis. In a previous chapter, we used static force analysis to obtain all laws in mechanism. Dynamic effects are neglected to simplify the analysis. However, most mechanisms actually are not static, and some cases cannot ignore dynamic effects. In this chapter, to approach real problems, dynamic force analysis is conducted for mechanism. Here, section 15.2 and 15.4 will be skipped. We will talk about how to use free body diagrams and the conservation of power to solve the dynamic problems. These two methods are actually similar to laws mentioned in static force analysis. In the subject of machine dynamics, we bring together kinematics, the study of motion and the geometry, with kinetics, the study of the relationship between force and motion, to obtain information on the forces and the torques acting on moving machining. Two major failures modes of machine members are fracture and deformation. They are caused by excessive stress and elastic deflation. And the forces and the torques are essential to calculating the stress internal to the members of the machine and the elastic deflations of the members. Here, accelerations and the angular accelerations of machine members are involved. Before studying dynamic force analysis, they need to be calculated using methods described in Chapter 7 of textbook. Accelerations are related to the laws acting on those members by Newton's second law. Sir Isaac Newton was a British mathematician, physicist, and astronomer. He stated three famous laws of motion in the mid-1680s. Among them, Newton's second law described the effect of the net force and the mass on the acceleration of an object. The acceleration is proportional to the total applied force on the object. And all the laws of motion extend Newton's laws of motion for point particle to rigid body motion. They were formulated by Euler about 15 years after Isaac Newton formulated its laws. For translation motion of rigid body, sum of all the external forces acting on the body is equal to the body's mass times the acceleration of its mass center G. We also call this equation as Newton-Euler equation. For a rotational motion, a moment of you can say a torque causes an angular acceleration. The angular acceleration of object body is proportional to the total applied moments on the object, where Ig is moment of inertia of the body about its mass center G. Later, we will use these two equations to handle the dynamic force analysis. For a dynamic analysis, we need to know the famous D'Alembert principle. D'Alembert principle also is known as the Lagrange-D'Alembert principle. It is a statement of the fundamental classical laws of motion. We can say D'Alembert principle is another way of writing Newton's second law. Let's see Euler laws of motion. The left side of the equation is total force or moment, and the right side is the kinetic reaction. For translational motion, the kinetic reaction is the mass times acceleration of the body. And for rotational motion, it is the moment inertia times angular acceleration. To move the kinetic reaction to the left of the equation, the principle states that the total external forces or moments and the kinetic reaction acting on a body equals 0. D'Alembert's principle makes this dynamic problem look like a static problem by defining an initial force and the initial moment. Initial force and the initial moment always equal in magnitude to kinetic reactions, but in the opposite directions. An example is a precision vehicle that is accelerating in a forward direction. Passengers perceive that they are acted up by force in rearward direction, push them back into their seats. In other words, using inertial force and inertial moments as fictitious force and moments, we can simplify the dynamic problem into the static problem. Therefore, the method adopted in static force analysis, free body diagrams and the conservation of power, for example, can be applied in dynamic force analysis.